is something that's extremely interesting to me anyway. If you do science, you know that you might have something that is a complicated curve, but all you have to do is plot it on fancy paper, like log paper, log paper, and you can often straighten out things that look complicated. And that model really works in machine learning. It turns out that almost anything can be turned into a straight line by just modifying the input data, take the square of it, the cube of it, multiply it together, the log of it. If you can make it a straight line, then you can just fit a straight line separator in a space that is derived from the input data. So support vector machines are powerful and incredibly easy to do. So here, I want to sort the red dots from the green dots. Well, either of these lines would do, right? They'll separate it. So the question is, what is the best separator? Well, the best separator is the one that has the widest margin. So you choose the line that gives you the widest margin between those two, and that's the solution for the best line to separate these two. And that line depends only on these points right here, right at the edge. So if you remove or change these green dots, it has no effect at all. These are what's called the support vectors, and you only need to include them when calculating the border. It's crazy how easy that is, and it's still quite powerful. So support vector machines are one of the more popular machine learning models. So I'm not going to do them live, I'll just talk about them. So here, you set this thing up, it prepares a situation like this with random dots. I've got red dots and blue dots, and I want to make a support vector machine. So I create a classifier support vector machine, and there's what it does. It finds it here. Now, we're going to see another problem I didn't mention about that California housing set. The scale of the data matters. So here is the line it made to separate the red from the blue. Well, that's fine, but suppose I measured y in a different unit. I'm going to multiply the y scale by 100. So now 0, 100, 200, 0, 1, 2. It's still the same data. You'd expect the same model. That's not what happens at all, because its measure of error is the error squared, the squared deviation from the right model. The width of the street is another measure. So you just told it that vertical distances count 100 times more than horizontal distances. So it cannot afford to miss vertically a little bit like it did here. It's going to move that line down to where the vertical error is much smaller than the horizontal error. And that's the problem when you start with real data like that California housing data, where you had populations and the number of rooms and the dollar cost of a house. Those came in with different scales. One of the things you typically have to do is normalize the data. If you want to weight these things equally, you have to normalize everything to a fixed range, like between 0 and 1, or minus 1 and 1, to avoid this. Otherwise, it's going to ignore a whole bunch of the data and overemphasize certain data that just happens to come in units that makes it look big. All right, and so that's one thing you could do. Now let's consider realistic data, like it overlaps. Now you cannot do support vector the way you talked about before, where you just take the edge points because there's some overlap, so you have to generalize it and accept some error and include more of the points. But the model can do that, so we can put a separator of those. Now what you can do is you consider a regularization parameter. And this is a big, important concept. I mentioned before the problem of overfitting. You want a model that learns the trend in the data, but you don't want to memorize the noise in the data. So what you want is not just a line that hits the points, you want a smooth line that goes through the points. So what you do is you add a parameter to the cost function, which penalizes it if the line starts getting too wavy. You put in some kind of smoothness parameter. And there are various ways to do it, but that's called a regularization parameter. So it's, again, kind of disturbing. Instead of following the data, follow my preconceived notion that I would rather see a smooth curve without a lot of wobbles in it, which isn't something that comes in from a human. So you have a parameter, and what you do is you just try various values of that parameter. This CC is the regularization parameter, and I just move it by a factor of 10 through many values. So at one value, the regularization is so bad, the model is completely wrong, it called all of them blue, so that's over-regularized. The only thing it did was avoid having a high slope, and it didn't pay any attention to the data at all. The 0.1, it's getting pretty good. 0.01, it's still pretty good. So there's a region where the regularization parameter does what I want. It still does a good fit to the data, but it makes it smooth. And so if I give it a curvy data set, like this one they call moons, where you can't draw a single line between them, now if you create and train the model, it can still do it because you use a polynomial fit. It will take high order powers of these parameters to make a different graph where the separation is a line and fit that line. So you've got, this is a polynomial, so you choose what order of polynomial to use, because if you think about a polynomial, you have like ax squared plus bx plus c. Well, that means if you had multi-dimensional graph paper that had x and x squared in it, that would be a straight line. So any polynomial can be turned into a straight line with that kind of transformation, and so you can fit this with a higher order polynomial. Now, the higher order your polynomial is, the more parameters and the more you can precisely spike this model. That's polynomial kernels can do it. So here you are doing, I think, a 3rd degree polynomial. Here you are doing a 10th degree polynomial, and you can see it's starting to do stuff which is kind of unreasonable, like go all the way over here. And this is why I mentioned something. You may remember in Donald Trump's first term, the pandemic hit, and there were something like 35 cases in America, and then there were a few hundred cases, and he went on TV and said, it's going to go away by Easter. In 3 weeks, it's going to fall to zero. It'll just be gone. And we all wondered, where did that come from? That came from a financial analyst on his team who did projections for money using Excel. And what Excel can do is you have some data, it can fit polynomials through the data. And so it fit like a 10th order polynomial through the data, which waves all over the place, and did go to zero by Easter, following the noisy data. That's a failure to regularize it. It fit the noise in the COVID cases to that point without being normalized to follow what was more likely the trend. And that's the problem here. And again, it's human judgment, how much of that stuff you want to do. All right. Let me